Hello everyone and welcome back to another video. In this video, we're taking a look at adding and subtracting rational expressions. Before we get to how we can accomplish that, we should first understand a few things. First, we need to understand prime factorizations. We also need to understand, I suppose, what a prime number is, because we need to know what prime numbers are in order to understand what prime factorizations are. And then we need to know about how to calculate what's called the least common multiple. Oops, redo. I'll retype that. Least common multiple. So these are the three pieces that we need to ultimately understand in order for us to be able to add and subtract rational expressions. So first, what are prime numbers? Well, some examples of prime numbers are 2, 3, 5, 7, 11, 13. I could keep going with this list. But notice there's no obvious pattern, but what characterizes prime numbers is that for each of these numbers listed, the only things that divide them are 1 and their self. So 2 is just 1 times 2. There's no other way to express 2. 3 is just 1 times 3. There's no other way to express 3, and etc. for each of the primes. So that's what makes a number prime. Also, just note that 2 is the only even prime number, and the rest of the prime numbers are odd. Next, prime factorizations. It's a theorem called the fundamental theorem of arithmetic, and it tells you that every integer can be broken down into products of primes. So we can take any integer we want, and we can find its prime factorization. So why don't we look at an example? Let's suppose we want to take the prime factorization of, let me move this down. Say we want to take the prime factorization of the number, let's just go with something like 60. Alright, we want the prime factorization of 60. Well, we can break it down in the following way. We can write 60 as 2 times 30. Notice that 2 is prime, so I will circle it. 30 is 2 times 15. 2 is prime again, so I circle it. And 15 is 3 times 5. 3 and 5 are both prime. I circle both of them. Okay, now we can more compactly write the prime factorization of 60 in the following way. We can write it as 2 squared, that's because there are 2 2's listed, times 3 to the first power, because there's 1, 3, times 5 to the first power. You can check that 2 squared times 3 times 5, 4 times 15 is 60, so this does check out. So we've got the prime factorization of 60 here. Now, we want to use our knowledge about prime factorizations to understand what's called the least common multiple. Before we get into that, I want to show you how we approach this in class, just for you to recall that. So let's suppose that we want to find the least common multiple of, let's suppose the two numbers are, how about 9, I don't know, let's use 24. I want them to be kind of random. 24 and say 90. Somewhat big, somewhat random. Well, the first thing we'll do is we'll find those prime factorizations for each number. So that's going to come up directly immediately. So for 24, the prime factorization, we get 2 times 12. We get 2 times 6. And then 6 is 2 times 3. Notice I've circled all the prime numbers again. So 24 is, there are how many 2's? There's 1, 2, 3 2's, so I write 2 to the third times, and then there's only 1 3, so I write 3 to the first. So that's the prime factorization of 24. Similarly, the prime factorization of 90, we get, well, you can think of 90 as, you could do 2 times 45. I'm going to do it a little bit different, though, just to show you, you don't have to always pull out 2. You could do 9 times 10. Notice I don't circle either of them, though, because 9 and 10, neither of them are prime. And then 9 is 3 times 3, so I circle those because those are prime. And 10 is 2 times 5. So, the prime factorization of 90 is then 2 to the first, because there's 1 2, times 3 to the second, because there are 2 3's, times 5 to the first, because there is 1 5. So notice we've got these two prime factorizations for 24 and 90 now. So maybe I'll box those just for reference. Okay, now we want to find the least common multiple. Well, the way we approached it before, kind of naively, just to recall what that process looks like, is we consider all the multiples of 24, and list them here. 24, I won't compute it this way, but I just want to remind you how we did it. These are the multiples of 24. I'll stop there. I don't know how far I have to go because I'm not going to calculate it this way anyway, but I just want to recall this. 90, 180, 270, 360. So at some point these lists are going to overlap one another. And you can see that even though we've gone out somewhat far, we haven't reached a common multiple yet. We haven't reached a common multiple, so we don't know what the least common multiple is using this approach yet. We would have to go out further. But thankfully, there's a way of avoiding this kind of listing process that we went over in class, and it uses prime factorizations. So let's go ahead and do that now. Let's use the prime factorizations we've been given. So what I'll write is I'll write the LCM, and I'll write it in this ordered pair kind of fashion. I'll say the LCM of 24 and 90. LCM is least common multiple, just to be clear. The LCM of 24 and 90. The way that we approach this problem is we take a look at both prime factorizations. So I look here to start. I can see that we have a power, we have 2 to the third as a factor of 24. We have 2 to the first as a factor of 90. When you're taking the least common multiple, it needs to be a multiple of the highest power given. So it needs to be a multiple of 2 to the third. So we need that in our answer. We need the highest power of 2 among both factorizations. So we take 2 to the third because that's the highest power that appears. Similarly, we look at the 3's in each factorization. The next prime number. 3 to the first is in this one. 3 squared is in this one. So again, we take the highest power. We take 3 squared. Lastly, we've got just 5 to the first here, and then we don't have a factor of 5 and 24, but again, that doesn't matter. We just take the highest power, which is 5 to the first, because the least common multiple, it needs to be a multiple of 5 in order to be a multiple of 90. Okay, so we've written down the least common multiple of 24 and 90. It's 2 to the third times 3 squared times 5. We can calculate this a little bit nicer and easier to tell what the actual answer is. We get 8 times 9 times 5, which is 72 times 5. which is, what is that? Is that 360? Right. So that is our least common multiple. Now, I'm going to pan over to the side, or to the bottom here. And now what we're going to do is we're going to use what we've just developed. Basically the least common multiple is what we built up to. That was the big thing that we wanted to take away from all of that, is how to calculate the LCM of two numbers, given that prime factorization we had above, that idea we had above. So now what we're going to do is we are going to look at an example where we apply the knowledge we just learned. So in particular, let's suppose that we've got 1 over 24 plus 1 over 90, and we want to compute whatever this is. So we want to figure out what this equals. Well, here's what we can do. We can take both fractions here. We can basically just take this entire expression and we can multiply the top and bottom by 360. That's the least common multiple. When we do that, we get 360. Actually, I take that back. Let's not multiply by 360 over 360. Let's make it so that way, get rid of these parentheses, let's make it so that way we'll end up with 360 in the denominator for both fractions. So maybe I'll pull this down, give myself a little bit more room. So I'm going to have to multiply 1 over 24 times something over something plus 1 over 90 times something over something. And now I need to think, 24 goes into 360 how many times? If you're not sure, that's fine. I think it works out to be 15. So I multiplied the top and bottom by 15. Notice I'm really just multiplying by 1. 15 over 15 is equal to 1. So I'm not changing the number, I'm just changing how it looks. It's still the same number, this is still legitimate. Similarly, I need to multiply 90 by something to get 360. I need to get the LCM, so I need to multiply by 4 over 4. Because 90 times 4 is 360. Okay, now, since we'll have 360 in both of our denominators, I'm just going to pan over here to the right, and I'm going to write this equals just a single fraction. It's going to be over 360 because that's our LCM. That's what 24 times 15 is, and it's also what 90 times 4 is. And then in the top we got 1 times 15 plus 1 times 4, which is 19 over 360. So we've added those two numbers together, and we use the least common multiple as our least common denominator in order to add two fractions that don't have the same denominator. I want to take the time to look at one more example where we've got some variables involved as well. Instead of just working with fractions of numbers, let's work with variable expressions. So let's pan down here. You can zoom out and see all that we've done so far. But yeah, let's zoom back in. Let's look at one more example. Let's suppose that we've got something like 1 over, how about 24 4x squared y plus, let's say, 3 over, let's make it 90 again. We'll just keep the same, so that way we know the LCM is 360 still. And then let's change these variables. Let's make this one xy squared. Okay. So this is what we've got. This is our example. We want to add these two together and write it as a single fraction. Well, first of all, remember that the LCM of 24 and 90 is just 360. So we want the LCM of 24 x squared y and 90 xy squared. Well, we already know the 360 will definitely be a part of the LCM because of what we concluded earlier. And now we need it. Remember the key idea. We always take the highest power of what appears. So we have x squared and x. So we take the highest power. We get x squared. Similarly, we've got y and y squared. But again, we always just take the highest power. And this guarantees that the LCM is actually a multiple. It's actually a multiple of y squared this way. So yeah, this is the LCM. So now what we need to have happen is we need to have this as our least common denominator. So just as before, I'll pull this down. I'll write this as 1 over 24. I'll just kind of rewrite it, but leave myself a little bit of extra room to multiply on the top and bottom by something. Okay, so now that I've done that, I've just rewritten that what's above and then left myself some room to multiply by something. Well, remember what we multiplied by before. We had our 15 to give us 360, so I'll put that there. 15 over 15. We're still going to have these parts of our answer as before, but we're going to have to include some variable bits as well. Well, ultimately, we want to get x squared y squared. Let's think about what we need over here in order to get x squared y squared. We've already got x squared y. So notice we're just missing one y. We need one more factor of y here. And then we'll have y times y, we'll have y squared. Similarly, over here, we've got xy squared, but we need x squared y. We need x squared y squared. So this x right here, in order to give us x squared, we need to multiply by another factor of x. Now, our final step, maybe final couple steps, is we can write this as a single fraction where 360 x squared y squared is our denominator. And again, that checks out from, if you wanted, you could check that 24x squared y times 15y is equal to 360 x squared y squared. And similarly, 90 xy squared times 4x is also 360 x squared y squared. But anyway, that's our LCM, so of course that's what our denominator is going to be. And so we just need to multiply across the top and add those two things together. In doing that, we get 15y plus 12x. And notice the way I started the problem is I had a 3 over 90. So notice we can actually factor out a common factor of 3. That leaves us with 3 times 5y plus 4x. And I can factor out a common factor of 3 out of the bottom as well. Those can cancel out. And so we really just have 5y plus 4x all over 120x squared y squared. All right, so we've been going for over 20 minutes now, so I think that's the end of this video. I just wanted to go in a little bit more detail about how we do these sorts of rational expression calculations. Please leave any questions that you have, or note a timestamp of where you get confused anywhere in this explanation, and I'm happy to answer questions that you have in class. But otherwise, happy mathing, and I will see you all in a future video.